Welcome back to The Explainer. A lot of people hear the word physics and immediately picture like impenetrable walls of terrifying math. But I want us to look at it completely differently today. Actually, scratch that. Physics isn't just numbers on a chalkboard. It is the language we use to describe our everyday world. It's the hidden rule book behind literally everything that moves, crashes, falls, and flies around us. So today, we're going to translate that rule book together. We're going to explore the absolutely incredible journey of energy.
Okay, let's dive right into our conceptual roadmap for today. We'll be covering the energy of motion, the work energy principle, gravitational potential energy, and finally, total mechanical energy.
All right, Section 1, the energy of motion.
Think fast, dynamic, and powerful. Whenever something is moving, it's packing a specific type of energy. We call that kinetic energy. The word actually comes from the Greek word kinema, which just means motion. It's the exact same root word we use for cinema, because they're moving pictures. By definition, kinetic energy is the energy possessed by moving objects, giving them the capacity to do mechanical work. Simply put, if an object is moving, it has the ability to apply a force to something else and displace it. It can literally move the world around it.
And this brilliantly illustrates the whole concept. Just picture a construction worker driving a spike into the ground with a massive sledgehammer. Before that hammer even hits the spike, it's swinging through the air, and because it's moving, it carries kinetic energy. The faster the worker swings it, the more kinetic energy builds up. And when it finally strikes, boom! All that kinetic energy goes directly into doing the mechanical work of physically pushing that heavy metal nail deep into the earth. More speed equals more energy, which equals a way deeper displacement of the nail. Now, to understand exactly how much energy we're talking about, we look at the math. And don't worry, it's surprisingly simple. EK equals 1/2 mv squared. M is the mass of the object, and v is its velocity or speed. But here's the absolute secret of this formula. Notice that the velocity is squared. This means that if you just speed up an object a tiny bit, its kinetic energy doesn't just increase a little bit, it literally skyrockets. And we measure this immense energy in a unit called joules, represented by a capital J.
Let's make that math super concrete with something you've probably seen. Imagine a professional baseball pitcher winding up and throwing a fastball. A standard baseball has a mass of about 150 grams. If that ball is traveling toward home plate at 35 meters per second, which is roughly 78 miles per hour, it carries exactly 92 joules of kinetic energy. That 92 joules is the exact amount of punch the catcher is going to feel right in their mitt. It's the pure energy of motion, it's quantifiable, and it is very real.
Moving smoothly to Section 2, the work energy principle.
So, the crucial point here is now that we understand the energy of motion, how does an object get that energy in the first place? What's the bridge? Well, that bridge is a concept known as the work energy principle. It states that the net amount of mechanical work done on an object directly equals that object's change in kinetic energy. When we talk about work in physics, we mean applying a force over a distance. So this principle tells us that work isn't just some abstract idea. Work is quite literally a transfer of energy. When you do work on an object, you are injecting kinetic energy right into it. I want to walk you through the logical ladder of how this works without getting bogged down in messy algebra. I promise. It really just takes 3 beautiful steps. First, we know from Newton's second law that a force causes a mass to accelerate. Second, from basic kinematics, we know that as an object accelerates over a certain distance, its speed increases. And third, when you substitute those ideas together, you find that the total work done, meaning that force applied over that distance, is mathematically identical to the newly created kinetic energy. A force applied over a distance perfectly creates that speed.
Let's apply this to a totally frictionless ice hockey rink. Imagine a 165-gram hockey puck just resting on the ice. A player sweeps in and uses their stick to apply a constant force of 5.0 newtons over a distance of half a meter. Now, force times distance equals work, so the player has done 2.5 joules of net work on the puck. Because of the work energy principle, we know those 2.5 joules instantly become the puck's kinetic energy. If we run that through our formula, it means the puck goes from completely still to zooming away at exactly 5.5 meters per second. The work from the stick literally became the speed of the puck.
Which brings us to Section 3, gravitational potential energy. Up until now, we've been talking about things zooming and smashing. But what if the energy is completely silent, just waiting to be unleashed? Consider an acrobat high up on a tower, about to jump down onto a seesaw to launch his partner into the air.
before that acrobat on the tower even moves a single muscle, while he's standing perfectly still right at the edge, he already possesses a massive amount of energy. Why? Because gravity is relentlessly pulling on him, ready to do the work of pulling him down to hit that seesaw.
This invisible, stored energy is called gravitational potential energy. It's energy an object possesses purely because of its position in relation to gravity. But here's the trick. It entirely depends on a reference level. You basically have to decide where the floor is. The designated reference level, say the ground, or even just the top of a table, is considered 0 joules. Any object lifted above that designated zero line immediately gains gravitational potential energy because it has the potential to fall back down.
Let's step back and see how this builds across completely different scales. Think of a downhill skier perched at the very top of an icy mountain. Their reference level is the bottom of the ski run, and gravity is about to turn all their stored potential energy into thrilling, high-speed kinetic energy. Now, completely switch gears and picture the space shuttle orbiting 400 kilometers above the Earth. That shuttle has an absolutely colossal amount of gravitational potential energy because its potential fall back down to the reference level of Earth's surface is just immense.
The story this formula tells is incredibly intuitive. EG equals mass times gravity times height. You've probably heard the old saying, the higher you go, the harder you fall, right? Well, physics literally proves it. If you increase the mass, or if you increase the height, you get a larger number of joules. You get way more stored energy. A heavier object, or a higher object, has the potential to do much more work when gravity finally pulls it down.
Now, what's really interesting about this slide is the gravity variable, g. We usually just say it's a constant, 9.8 meters per second squared, near Earth's surface. But it isn't actually a strict constant. If you go way up to where that space shuttle is orbiting, 400 kilometers high, you're obviously further from Earth's center. And at that altitude, g actually drops from 9.8 down to 8.5 meters per second squared. Gravity itself weakens the further you step away from the planet.
But bringing it back down here to Earth, let's anchor this math with a thrilling, real-world example, an amusement park drop tower ride. Imagine a 48-kilogram student strapped into the seat, slowly hoisted up 110 meters in the air. At the very top, before the terrifying drop even begins, their height and mass alone mean they are holding an incredible 52,000 joules, or 52 kilojoules, of stored gravitational potential energy. All of that energy is just sitting there, waiting for the ride operator to release the brakes.
And finally, Section 4, Total Mechanical Energy.
All right, we've mastered motion, and we've mastered position. Now, let's unite these two forms of energy. On one side, we have kinetic energy, the loud, active, visible energy of an object hurtling through space. On the other side, we have gravitational potential energy, the quiet, stored, invisible energy of an object poised above a drop. They're completely distinct, for sure, but they're intimately related.
Because when you put them together, you get mechanical energy. By definition, mechanical energy is simply the total sum of an object's kinetic energy and its gravitational potential energy. At any given moment, an object might have purely kinetic energy, purely potential energy, or a constantly shifting mix of both. But if you just add them up, you get the total mechanical energy of the whole system.
Let's run through 3 vivid examples to really cement how this works. Think back to our sliding hockey puck on the flat ice. It has 0 height, so it has 0 potential energy. Its mechanical energy is entirely kinetic. Now picture an acorn hanging quietly from a high tree branch. It has 0 speed, so no kinetic energy. Its mechanical energy is entirely gravitational potential. But now picture a parachutist halfway through their descent to the ground. They're falling fast, meaning they have kinetic energy, and they're still high up in the air, meaning they have potential energy. Their total mechanical energy is the sum of both that active motion and the remaining height.
I want to end this explainer with a quick thought experiment for you to visualize. Imagine holding a basketball and throwing it straight up into the air. What happens to its energy? Well, as it leaves your hand, it's moving fast, so maximum kinetic energy, but it's low to the ground, so very low potential energy. As it climbs, gravity slows it down, seamlessly turning that kinetic energy into potential energy. At the very peak of the throw, for a split second, it completely stops. 0 kinetic, maximum potential. And as it falls back down, that potential transforms perfectly back into kinetic energy. It's a gorgeous, seamless conversion of energy happening right there in your hands. So keep visualizing the physics all around you, keep asking questions, and we'll see you in the next explainer.